Okay, so we have been talking about virtually indexed, virtually tagged caches. Remember, right? So there is. So how does the whole system look? So there is address space. This is the virtual address space. So your program has an address that gets added to the segment base and you get an effective address here. This effective address essentially goes through a page translation mechanism and you get a physical address which you use to basically access your RAM. Okay? Right? In this part there exists a cache memory also. So a copy of this RAM is kept in the cache, right. So what we suggested yesterday or last class was that we can use this effective address to the cache, right. We can use this effective address to find out if, to see if it is, there is a map, right. We can index and find out if there is a entry here, okay. And by that what will happen? If there is a cache hit, I can forget this whole stuff. If there is a cache hit, then I can forget this whole stuff. If there is a cache miss, then I need to basically look into this. Now that means what I am going to store in the cache is the effective address. I am using the effective address to index into the cache. I am using the effective address to also do what? I am using the effective address as the bits of the effective address as the tag bits also, right. So essentially this actually comes as a thing. Okay. Now what would be the disadvantage of this? This is what we stopped last time. So what is the disadvantage of a virtually indexed, virtually tagged cache? Palgat, are you able to follow my question? Yes. Why is that S so low? Still low. Okay. Okay. Tell me, what is the disadvantage of having a virtually indexed, virtually tagged cache? When I want a write back policy, I am gone, right? I have to do a reverse address mapping to find out. So I need to have a reverse page table and all. Okay. So what is interesting for me is if I can do the indexing, if I do completely physically indexed, physically tagged cache, that means it will start here. Okay. Now the cache comes. Okay. Then it becomes extremely sequential. It becomes extremely slow. There is no advantage of having a cache, meaning I will not get that advantage of having a cache. Interestingly, what happens is this effective address is also, let me take the red pen here, is also having a bypass called this TLB, which you still remember, translation look aside buffer. Here itself I will get this physical address if there is a TLB. So, right. Now this is again indexing, right, and this is also indexing. So can I have something like a virtually indexed, physically tagged cache? Can I have a virtually indexed, physically tagged cache? That makes my life much more easier. In the sense, what happens is I get an effective address. When I am indexing into the cache to find out whether the entry to which it is hashing to, it's mapping to, is a valid entry or not, and retrieving the tag bits, then I get back the tag bits and only I compare. No, so I index using the effective address, and there I retrieve the tag bits. Are you getting? I retrieve the tag bits to find out what is it, and when I am retrieving the tag bits, at that point of time, by that same time, what would have happened is, if the effective address is also there in the TLB, I would have got the physical address also. So now this physical address I can compare with the tag bits that are coming here and say if it is a cache hit or a miss, right. So what happens is when I want to replace it back, I can reconstruct exactly the physical address, so I can implement a write back policy here. Are you able to follow this? So when a VIPT, so what happens, I am indexing into the TLB, at the same time I am indexing into the cache. So those two indexing are concurrent. By the time I am getting the tag bits out of my cache, at the same time if there is a TLB hit, I will also get the physical address out of the tag, right. Now I can physical address out of the TLB. Now I can go and compare the TLB and the cache out this tag bits, and now go and say if it is a hit or a miss. Are you able to follow what I am saying, right. So if I have a VIPT cache, then again I am getting the same advantage as a VIVT cache, and I get out of that major disadvantage of not able to implement or having additional circuitry to go and do a write back policy, implement a write back policy, wherein I want to move the cache data back to the memory, right. So this is the advantage. So VIPT is the one that is followed in modern current processors. Many of the processors, all of the processors use a VIPT. Now why does VIPT work? Okay, I told you, right, for lot of questions in computer architecture there are one word answer which will imply the answer. So why does VIPT as a concept work? VIPT is a success if I have what? If I have a TLB hit and a cache hit together, right. Now the way you should answer is why there is a chance of a TLB hit and a cache hit to be together. VIPT is a failure if there is a cache hit and a TLB miss, but will it happen at all? It will not happen, because whatever address that are stored in the cache is a subset of the pages that are stored in the TLB. It will be recently used. If you are going to look at replacement, cache replacement would be more than the TLB replacement, because the granularity there is 4096 bytes. The size of a page is much larger than the block of a cache. So there will be very remote chance. Probably I will ask as a question for you to think over in your end semester, remind me, that can there be a situation where there could be a TLB miss and a cache hit? Most probably it may not be, right. Okay. Are you able to understand what I am saying, right? So having a TLB miss and a cache hit is very remote, right, and that is why VIPT as a concept is much more successful. Fair enough? Okay.